For nearly 700 years, engineers across the Islamic world developed a way to cool entire cities without using electricity. They shaped wooden lattice screens with such precision that air moving through them could fall by 8 degrees Fahrenheit. The same aerodynamic principles once used in Mamluk palaces and Mughal mausoleums can now be recreated with $30 of plywood from Home Depot. Modern computational fluid dynamics testing has verified the effect. By the end, the reason this architectural method vanished from Western construction will become clear, along with how the system can still be recreated today. This structure was known as the mashrabiyah. The term originated from an Arabic root connected to drinking water. In its earliest form, it described a small shelf positioned beside a window where porous clay jars were placed behind carved wooden screens. Passing air cooled the stored water through evaporation. Over generations, the design evolved into something far more advanced. The mashrabiyah became a projecting upper-floor window enclosed completely with hand-carved latticework. These structures spread across the Islamic world from Baghdad to Cairo to Jeddah. Yet the purpose was never ornamental alone. Egyptian architect Hassan Fathi dedicated years to examining these screens throughout historic neighborhoods in Cairo. In his 1986 publication, Natural Energy and Vernacular Architecture, Fathi described 5 separate functions working together inside a single mashrabiyah panel. It regulated incoming light. It directed airflow, it lowered the temperature of entering air, it raised humidity levels in dry environments, and it protected privacy from the street below. 5 separate mechanisms existed within one carved wooden structure. Fathi documented these screens in locations such as Beit al-Suhaimi, a residence constructed in 1648 along the ancient streets of Islamic Cairo. He photographed the lattice patterns, studied air movement, and warned that modern architecture was abandoning centuries of proven environmental physics in exchange for glass, steel, and mechanical air conditioning systems. His own architectural work combined elements from Cairo's vernacular urban traditions, including the mashrabiyah, the Malkaf windcatcher, and the Salsabil fountain. Most architects ignored the warning. The mashrabiyah also appeared outside the Arab world. In Iraq, it became known as shanashil. In Iran, mushabak. In Yemen, taka. Across India, builders used the jali, meaning net, a perforated lattice screen carved into stone or other materials throughout Indo-Islamic architecture. From the Alai Darwaza, built in 1305, to the marble lattice screens inside the Taj Mahal, the same concept appeared repeatedly. Civilizations that mastered extreme heat discovered the same engineering independently. Baghdad, Cairo, Jeddah, Delhi, Agra. Even Mediterranean Europe adopted it. In Spain, the structure became celosia. In Italy, gallosia. 5 centuries of environmental engineering spread across multiple continents. The physics behind the design was more advanced than most people realized. When wind strikes a solid wall, it diverts away. When it passes through an open window, little changes. But when air encounters a mashrabiyah, it must travel through hundreds of tiny openings. Every aperture functions like a miniature compression chamber. Both Bernoulli and Venturi principles operate simultaneously. As air is forced through narrow gaps, velocity increases. Once the air expands again on the interior side, pressure and temperature decline. The result is a cool indoor breeze even when outdoor wind barely moves. In arid climates, such as Rajasthan and India, craftsmen carved smaller perforations to intensify the Venturi effect and strengthen evaporative cooling. In humid regions like Kerala, wider openings encouraged stronger ventilation instead. The geometry changed according to local climate conditions centuries before modern instruments existed to measure airflow behavior. Adding water transformed the system even further. The earliest mashrabiyahs held clay water vessels directly behind the latticework. Air passing through the screen moved across moist, porous surfaces, reducing temperature through latent heat absorption. The wood itself played an essential role. Natural wood fibers absorbed, retained, and wicking moisture in a process similar to plant evapotranspiration. The screen effectively became a breathing, cooling membrane integrated into the building itself. The impact on sunlight was equally significant. Parametric simulations demonstrated approximately 14% lower operative temperatures, along with a 77.8% reduction in peak solar gain. Additional studies reported that direct solar radiation declined by nearly 18%, leading to a 43% drop in energy consumption. Indoor air temperatures fell between 4 and 4.8 degrees Celsius. On southern facades, cooling loads decreased by 21%. Western facades saw reductions of 17%. Eastern facades achieved 13%. A 78% reduction in peak solar gain came from nothing more than a carved wooden screen. These laboratory measurements were later confirmed through computational fluid dynamics analysis. Ancient builders never possessed simulation software. What they had instead was centuries of experimentation across 3 continents. The earliest recognizable mashrabiyah designs appeared during the 12th century in Baghdad under the Abbasid period. Narrow streets filled the city. Buildings rose on both sides while projecting lattice structures overhead created shaded corridors that directed airflow through the streets below. The Mashrabia was never simply a decorative window feature. It functioned as urban infrastructure. Entire neighborhoods were organized around the airflow patterns these structures generated. During the Ottoman era, from 1517 through 1805, the Mashrabia spread widely across the region. Nowhere did the craft become more refined than in Cairo. Walking along Al-Muizz Lidin Ala Al-Fatimi Street today is like entering an open-air museum devoted entirely to lattice engineering. That ancient corridor contains countless architectural variations, including wooden lattice windows that operate like breathing membranes attached to every structure they cover. Sunlight enters as soft, geometric shadows stretching across stone surfaces. Air circulates naturally through entire rooms without any mechanical equipment. In Saudi Arabia, the city of Jeddah became a full-scale testing ground for this technology. The historic quarter preserves more traditional Mashrabia screens than anywhere else in the region. At the center of Old Jeddah stands the Beit Nasif. Its lattice panels remain intact. They still function. They still cool interior spaces exactly as they did centuries earlier. Modern researchers later returned to this structure with scientific instruments, and the measurements they recorded changed the entire discussion. In India, the Jolly reached extraordinary levels of refinement under the Mughal rulers. At the Taj Mahal and at Fatehpur Sikri, marble lattice screens were carved with such precision that they filtered sunlight into highly detailed patterns while maintaining uninterrupted airflow. Research examining lattice applications in Indian buildings documented passive cooling effects that lowered indoor temperatures by approximately 5 degrees Celsius. At the St. Andrews Institute, architect Sachin Rastogi created a Jolly-style facade using rotated brick geometry. The structure reduced solar glare by 70% and lowered energy consumption by 35%. Every civilization living in extreme heat eventually reached the same conclusion independently. Persians, Egyptians, Ottomans, Mughals, even societies along the Mediterranean coastline in Europe. Then, within less than 1 century, the entire system nearly disappeared from construction. In 1902, Willis Carrier introduced mechanical air conditioning inside a printing facility in Pittsburgh. By the 1920s, his company promoted air conditioning as a symbol of progress and modern life. Advertising campaigns openly portrayed passive cooling methods as primitive and unsanitary. The machine era had arrived, and older systems were pushed aside. Across the Arab world, demolition programs accelerated. Mashrabias, along with many defining elements of historic Islamic architecture, were removed during modernization campaigns beginning in the early decades of the 20th century. In Baghdad, artists and architects watched entire historic districts disappear under wrecking crews. Architect Rifat Chadirji and his father traveled across Iraq and Saudi Arabia carrying cameras, documenting buildings before they vanished permanently. Throughout Saudi Arabia, traditional indigenous architecture gave way to sealed Western-style buildings covered in glass curtain walls. The contradiction was severe. Buildings were sealed shut to operate air conditioning systems, destroying the natural airflow channels that allowed the Mashrabia to function in the first place. Modern homes throughout the region now depend on complete separation from outdoor air in order to regulate indoor temperature mechanically. The solution created the exact problem it claimed to eliminate. The financial scale reveals another layer. The United States residential HVAC market reached a value of $15.4 billion in 2024. In 2020, electricity used for air conditioning represented roughly 19% of all electricity consumed in American homes. That totaled 254 billion kilowatt hours in a single year. Heating and cooling together account for approximately 55% of energy usage inside a typical American house. Imagine corporate executives seated inside boardrooms while lobbyists move through government offices. A $30 lattice screen capable of lowering cooling loads by 21% cannot sustain an industry dependent on multi-thousand-dollar systems consuming thousands of watts. Every Mashrabia installed represents one compressor never sold, one refrigerant refill never purchased, one maintenance contract never renewed. The technology was never disproven. It simply became economically inconvenient. Yet the underlying physics never stopped functioning. Modern scientists have now measured exactly how effective the system remains. In 2020, researchers from the University of Nottingham partnered with teams in Saudi Arabia for a major field study conducted at the Beit Nasif in historic Jeddah. They selected a building where the original Mashrabia screens remained fully preserved. Calibrated instruments were installed during peak summer conditions, while outdoor temperatures ranged between 40 and 41.6 degrees Celsius. That exceeded 106 degrees Fahrenheit under direct outdoor heat. The measurements confirmed what generations of builders already understood. The Mashrabia alone lowered indoor temperatures significantly. Researchers then introduced a simple modification. They suspended a wet cloth facing the Mashrabia from the interior side. This single adjustment reduced average room temperature by as much as 6.8 degrees Celsius. The indoor average fell to 33.8 degrees Celsius, while outside temperatures remained at 41.6 degrees Celsius. That created a temperature reduction of nearly 14 degrees Fahrenheit using nothing more than carved wood and damp fabric. No compressor, no refrigerant, no electricity bill. In separate studies, researchers used computational fluid dynamics software known as ANSYS to simulate airflow through multiple three-dimensional lattice geometries. The simulations demonstrated that lattice windows containing rounded surfaces generated pressure differences capable of actively drawing air through the screen even under weak wind conditions. A hexagonal lattice configuration optimized through evolutionary modeling reduced annual cooling energy consumption by 12.3%. Then came proof at skyscraper scale. In Abu Dhabi, the Al Bar Towers contain the largest computerized dynamic facade system on Earth. The entire concept was derived directly from the Mashrabiyah. More than 2,000 umbrella-like exterior elements on each tower automatically open and close according to the movement of sunlight. Solar gain across the building envelope was reduced by 50%. Massive glass surfaces continuously fold and unfold along the exterior of a desert skyscraper, reviving a cooling principle developed centuries earlier. A multi-million-dollar tower now demonstrates the same physical principles that a medieval carpenter in Baghdad once created using only hand tools at no cost. In New Delhi, the Punjab Kasari headquarters uses a glass-reinforced concrete jali facade. The double-layered lattice lowers interior temperatures while improving airflow, dramatically reducing air conditioning expenses. Billion-dollar skyscrapers, peer-reviewed research, and computational simulations now verify what craftsmen in Baghdad already understood 900 years ago. The debate is no longer about whether the system works. The real question is how to construct one yourself. The central principle is the perforation ratio. Research has shown that a 50% void ratio on south-facing windows provides the most effective balance between cooling efficiency and light control. Traditional builders followed this principle intuitively. When a Mashrabiyah faced the street, spacing between balusters became tighter at eye level to maintain privacy. Higher sections used wider gaps to increase airflow near the ceiling where heat accumulated. For homeowners, the target should remain between 40 and 50% open area. Narrow spacing works best where privacy matters most. Wider openings near the top maximize air circulation. The materials are simple. Wood has always been the primary traditional material because it controls shadows, reduces glare, tolerates high temperatures, and moderates humidity by absorbing moisture. Modern equivalents available from hardware stores function just as effectively. Cedar strips from a lumberyard cost between $15 and $20. Birch plywood can be cut manually with a jigsaw or processed on a CNC machine. Pre-built MDF lattice panels from Home Depot range from $12 to $30 depending on dimensions. A fully functional Mashrabiyah screen can be assembled using basic dowel rods for less than $30 in total materials. Wood should always come first because of its passive environmental benefits. Untreated softwood delivers the highest thermal performance. The material absorbs moisture from surrounding air and releases it gradually, adding passive dehumidification to the cooling process without consuming energy. Whenever possible, use softwood. The construction process is straightforward. Measure the window opening first. Build a frame using 1x2 cedar or pine boards. Form the lattice using 3 1/8" to 1/2" dowel rods, spaced approximately 1 1/2 to 2 inches apart. Secure connections using wood glue and brad nails. Sand the surface until smooth so airflow moves without turbulence. Attach the completed screen to the window frame with L brackets or friction fitting. For more complex geometric patterns, create the design using free CAD software and cut the pattern from 1/4" plywood with a scroll saw or at a local makerspace using a laser cutter. Either approach still keeps material costs below $30. Then comes the force multiplier. Add evaporative cooling. The Beit Nassif study demonstrated that the Mashrabiyah by itself produced a 4.8 degrees Celsius reduction. Adding a wet cloth behind the screen increased the reduction to 6.8 degrees Celsius, nearly 14 degrees Fahrenheit of total cooling without electricity. Hang damp muslin or burlap behind the interior side of the lattice. Another option is placing an unglazed terracotta container filled with water on the interior window ledge. Air crossing the lattice passes over the wet surface and loses heat through evaporation. On extremely hot days, re-wet the cloth every few hours, or install a slow drip system using a small water reservoir positioned above the fabric. Ancient Persian builders used this exact method with clay vessels. The same effect can now be recreated using a plastic bottle and cotton wick. Placement inside the house also matters. Install the screen on south-facing and west-facing windows first. The south facade provides the largest cooling load reduction at 21%. West-facing windows rank second. East-facing windows follow third. Northern exposure is generally unnecessary for cooling. Even apartments with windows on only one side can still benefit. Computational fluid dynamics studies confirmed that lattice screens installed in single-sided ventilated spaces generate enough pressure difference to draw air through the opening, even without cross-ventilation. That makes the system ideal for apartment residents who assumed passive cooling could never work in their layout. For off-grid cabins and homesteads, combine the Mashrabia with thermal mass walls and nighttime ventilation. No electricity becomes necessary. The screen effectively replaces both window coverings and air conditioning systems at the same time. Climate determines the final adjustments. In hot and dry regions, such as Phoenix, Las Vegas, or Tucson, tighter lattice spacing combined with evaporative elements provides maximum cooling. In humid environments like Houston, Miami, or Savannah, wider openings work better and water should be avoided. In humid conditions, the objective shifts away from evaporative cooling and toward accelerated ventilation. Additional moisture is unnecessary when air is already saturated. Ancient builders always adjusted geometry according to climate conditions. The same principle still applies today. Every American house with a south-facing window already contains $30 of passive cooling potential sitting inside the lumber aisle. The physics were carved into stone in Delhi during 1305. They were turned on wooden lathes in Cairo during 1648. They were measured and validated through computational fluid dynamics at the University of Nottingham in 2020. They were scaled into skyscrapers in Abu Dhabi using more than 2,000 moving panels. The system works. It always worked. The Mashrabia was never obsolete. It simply became inconvenient for industries profiting from dependence on compressors, electricity, and recurring service contracts. The lattice requires none of those things. No compressor, no refrigerant, no permit, no electrician, no $14,000 installation. It only requires what it always required: wood, air, and the geometry perfected by Islamic engineers 7 centuries ago. That knowledge survived because physics does not respond to advertising budgets, lobbying campaigns, or modernization programs. Build the screen. Let the air handle the rest. If this story changed the way you see architecture and energy, share it with someone who still believes cooling always requires electricity. The technology already existed centuries ago. Most people simply stopped looking up at the windows. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.